So these derivations are really helpful in case you forget the formulas or the equations when you're taking an exam, but also as you're preparing for an exam, as I stated in the previous videos, it's helpful to deepen your understanding of the formulas by deriving them, because you understand where they come from, you get used to writing them, and so on and so forth. Now, the way I used to remember this when I was taking trig was let's start with sine. Okay, so the sine, let's go back to the double angle formula. Some people, sing the song, sine, cosine, plus cosine, sine. And then you just plug in the angles, and it always works out that way. So that's quick, right? That's a quick way if you want to memorize. Like I said, I like doing the math, so it really helps you as you advance in your mathematical studies. All right, so cosine, there's also a pattern for cosine also. Okay, that's just cosine, cosine, minus sine, sine, and then I used to just drop the angles in. So there's patterns, right? So always look for patterns when you're studying mathematics. That's one of the definitions, right? Mathematics is the study of patterns, space, structure, but ultimately it's geometry. It all breaks down to geometry. It's the study of shapes. Okay, at any rate, these are the sum of angle formulas, and we're going to use these to derive the double angle formulas. And now the double angle formulas, we'll get a couple of identities from those. Okay, so sum of angle formulas. Okay, and let's use these to derive the double angle formulas. Okay. So we're gonna rewrite the sum of angle formulas, but this time we just have one angle, right? It's just theta. This is one angle. You don't have to use the subscripts or the indexes. It's the same angle being added to the same angle. Okay, so that equals the sine. You can put a 1 here, a 1 there. That's just the sine of twice or 2 times theta. Because the angles are the same. All right, so all we have to do is let's rewrite the sine, cosine, cosine, sine. Okay, so sine, leave some space here, cosine, plus cosine, sine, cosine, sine. And then all the angles are the same. So we note here that, right, sine times cosine is equal to cosine times sine, because multiplication is commutative, right? So we could combine those two terms and just write it as 2 sine theta times cosine theta. I think that brings us up to number 9. Okay, the same, we're going to compute the cosine function. We'll rewrite it over. Cosine twice the angle equals cosine, cosine minus sine, sine. We'll drop in the angle symbol. And then note, we're multiplying cosine times cosine. So by definition of the exponent, we can write that as cosine squared theta. And the same deal, we have sine theta times sine theta. So we can just write that as sine squared theta. And that brings us up to number 10. Okay. Now from equation 10, we can derive two more identities because we can substitute, as we did earlier. We've already solved for equation 1, we solved cosine squared theta, which is equal to 1 minus sine squared theta, and sine squared theta is equal to 1 minus cosine squared theta. So we could squeeze, extract, manifest two more identities from this one, okay? So give a little extra space. Let's do cosine theta first. So cosine squared theta is equal to 1 minus sine squared theta minus sine squared theta. Like I said, whenever I substitute, I like to use parentheses. It really helps. So we have a minus sine squared theta here, and we have a minus sine squared theta. So we can add those two together. And what does that yield? That yields 1 minus 2 times sine squared theta. That brings us up to, let's say, 10.1. Since they're just variations, but you can also say the double angles are a variation of the sum of angle formulas. And they're all just variations of these two. Again, okay, when we let r equal 1, we're going to get 1 equals x squared plus y squared. And when we sub in our sine, x equals sine theta and y equals, x equals cosine theta and y equals cosine theta, we get cosine squared theta plus sine squared theta equals 1. And we know sine of theta is equal to y over r. And if we know sine, then we know cosine. Okay. Okay, that's in the first video. Just a bit of review, just to bring us up to speed. All right, let's now derive 10.2. Okay, there we go. Okay, so these are the only equations that we've employed thus far. Okay, so with that said, let's now substitute 1 minus cosine squared theta for sine squared theta. So I'm gonna, let me write that over. All right, so substituting for sine squared theta, 1 minus cosine squared theta, we get 1 minus cosine squared theta, and we're going to add this since, well, first we're going to simplify this because we have a -1 outside, so we want to multiply -1 times 1, which gives us +1, and then -1 times negative cosine squared theta is going to give us, back up, that should be a -1, okay? So we have a -1 here. So -1 times +1, that's going to give us negative 1, and then negative 1 times negative cosine squared theta is going to be positive cosine squared theta. So we can add these two together and we get cosine, 2 times cosine squared theta minus 1. Okay, so that's 10.2. Or you could say 11 or 12, whatever order you want to get to. But by number, that brings us up to 12. We've done 12 derivations, just using really 2 equations. So just to give you a preview for what's coming up in the 4th installment is we're going to use the double angle, these formulas. Okay? We're going to solve for cosine squared theta in 10.2, then we're going to solve for sine squared theta in 10.1. We'll do this one first, then we'll do this one. And then we'll come up with we'll develop the half angle formulas. Okay, so that's coming up next. Oh, disclaimer. Some of you may be wondering, what about the tangent functions? Well, the tangent functions, since they're just the ratio between sine of theta and cosine of theta, the tangent functions can be derived using the sine and cosine functions. Okay? And I'll do those in a later video.